Here's another video to the lecture Intro PDE. In this video we present section 2.3. This is rather small. So the section is called Existence of Solutions, and we present, the content is we present an example of a PDE with smooth coefficients. So with smooth coefficients which has in the neighborhood of 1 point no solution at all. So this shows the difference, that there is a really big difference between ODEs and PDEs. Because the theorem of Picard-Lindelöf's tells us that there does not exist such an ODE. By the theorem of Picard-Lindelöf, there, I think it's with double F, there does not exist an ODE with these properties. So smooth coefficients but no solution. Picard-Lindelöf gives us locally solutions, unique solutions of the initial value problem. Okay, so this is the content of the lecture today. So here the example is we first present this with complex coefficients, but later we will see that from this example we can easily deduce also an example with real coefficients. Here it's an example with complex coefficients in first order. Okay, so but the methods of the last section do not apply, because the last section last chapter we considered a scalar real first order PDEs. So this does not mean that all systems of PDEs and a complex first order PDE should be considered as a real system, or that can be also rewritten as a real system of PDEs, with two unknown functions. Real part and complex part are then the unknown functions. Okay, so in particular, this one should keep in mind, first order systems of PDEs. For this there also do not exist a general method, because one can more or less transform any PDE into a system of first order PDEs. Okay, so the PDE has this form, du by dx. So it's u is a function on R2 parameterized by x and y, and we have this differential equation. Here u is a complex function and f is a smooth function, and f should have two properties. First of all, it should be symmetric. Also if we in x, if we change the sign of x, it should take the same value. And the second property is if we that there exists circles smaller and smaller such that f vanishes, yeah, on a neighborhood of these circles. Yeah, so in a tubular neighborhood of these circles, maybe I write this here. I write this in this form. Yeah, in a neighborhood, they vanish. Yeah, I indicated in this form, and so on. Yeah, okay. Of course, these neighborhoods should become smaller and smaller such that they do not overlap. And okay, now, but the function, yeah, but okay. How is it clear that there exists such a function? Yeah, let us first explain that there always exists such a function. And we claim if h, if h real numbers to real numbers is periodic, positive, yeah, we assume that it maps not to the real numbers but to the non-negative numbers. Is periodic and vanishes, so on an interval, periodic and vanishes on an interval, but not everywhere. Okay, so how this should look like. Yeah, here if we have our variable x, one-dimensional variable, and here we draw h, so it should be periodic. So here it's for some interval it's 0, it should be smooth, then here again 0, then 0, then smooth, and so on. Yeah, and okay, such a function exists. Yeah, this is clear. Here it should be always constant 0, but in between positive and periodic. Yeah, periodic. Now, if we then take this function here, yeah, if we then take f of x is equal to exponent of minus 1 over x absolute value times h of 1 over x value, then this function has this property. Okay, first observe that we since this is periodic, yeah, we have at 0 there accumulates such periods, yeah, because of course the length, the periods become larger and larger. Yeah, they can look, for example, we can look at the values of n times some value, then some of these values, then in the first period, then we always get the same values. So this intervals, they accumulate. If we take the inverse, they accumulate nearby 0. And this factor, yeah, hopefully you know this from analysis 1. Since the exponential decay is much faster than the power decay, and this factor ensures that this function here is really smooth at 0. Yeah, this may f is smooth at 0 by this factor here. This factor. Yeah, this factor here. Okay, and this shows us that we have a sequence which behaves like 1 over n, roughly speaking, this radia which go to 0. So such a function really exists with these properties. Yeah, and since our function only depends on the absolute value here is of course the length. Yeah? X is length. Yeah, and also in these 2 coordinates, one should say, yeah, here x is the vector xy, so here this should be considered as the vector xy, and this is the length, okay, of this these 2 vectors. Okay, so we have such a function, so they exist. And now the claim is, yeah, we claim that there exists no solution in a neighborhood of xy equals 0, 0. Okay, and this we will prove in 3 steps. Yeah, we will need 3 steps. Okay, in the first step, yeah, by this condition, yeah, if you look at this equation here, yeah, also we reverse the second one, then this changes the sign, and this changes the sign due to this x in front of. So everything changes sign, so this is also a solution. Yeah, also if u is a solution, this is also a solution. So we may replace u by this. This is then also a solution. And if this, so whenever we have a solution, we have this solution, and then since the equation is linear, we also now not, also it's not completely linear, but inhomogeneous, yeah, due to the 1/2. We get that this is also a solution. And this expression, of course, now has this symmetry. So this means whenever we have a solution, we obtain a solution with this symmetry. So now it's enough to show that there does not exist a solution with this symmetry, because from step 1 we see that whenever we have a solution, there exists a solution with this symmetry. Now we claim, yeah, that all solutions vanish on these circles. Yeah, they vanish on these circles. Yeah, so in this example, they vanish along these circles here. This is the second step. Okay, now we make a transformation. Yeah, we transform this annuli, yeah, this yellow annuli, we transform by this equation. So this means we slightly stretch the x coordinate. Yeah, so second step, yeah, we have in the xy coordinates, yeah, we have our circles, and now we transform them in the sy coordinates, s has this property. This is x squared half for x larger 0 and minus x squared half for x smaller than 0. Now if we draw in these coordinates the circles, then the x coordinates, of course to the right, we have here the x coordinates and here the y coordinates. And now if we do here the same with the s coordinate and the y coordinate, then we see the y coordinates goes with becomes this y coordinates, for very small y, x squared is of course much smaller. So we contract the this direction, so it will look like ellipses. Okay, so in this we just stretch this. Okay, and then we calculate in this new coordinates this differential equation, and then we see that this new function, which is just the old function with respect to this new coordinates, that this new function now fulfills this differential equation. And this differential equation, these are, okay, so this you should know if you know the lecture function theory. Now we need some results of the lecture function theory, complex function theory. Because this equation, if this is 0, this exactly means that this function is in the complex sense differentiable. So this means this function is differentiable in the complex sense, and then by a result of complex function theory, one knows this is analytic. So U tilde is complex differentiable. In the sense of complex function theory. Of complex function theory. And then by the theory of complex function theory, very nice lecture by the way, we obtain U tilde is analytic. This follows from Cauchy's integral formula. This is a classical result, well known. Okay, and since this function has this symmetry, we have this symmetry along this axis. Okay, I didn't draw here this axis, but this means this function vanishes here, and then it also vanishes here. So along this line, U tilde vanishes along this line. Now by Schwarz reflection principle, sorry, no, not completely, but only in a small neighborhood here and here. So this vanishes, sorry, it vanishes along this complete line, and okay, and this implies that that U vanishes on this whole domain by Schwarz reflection principle. Yeah, since U tilde vanishes on the line S equals 0, again another tool from complex function theory by Schwarz, I think with T set, it's another Schwarz reflection principle, in Klammern of complex function theory, U vanishes on this domains, yeah, on A tilde plus. Yeah, and on A tilde. Yeah, so it vanishes here on A tilde. This is this whole domain. Yeah. Okay, and now we get a contradiction by the divergence theory. Yeah, now we get a contradiction by the divergence theory. Yeah, because if we calculate this integral, yeah, which is clearly non-zero. Yeah, so we integrate now in the original coordinates the integral over such a ball whose radius is exactly one of this radii with this special property. Sorry, yeah, and then this is non-zero, this integral. This is non-zero. Then this should be this expression. This we can write as the divergence of this expression. So by the divergence theorem, it should be the integral of this scalar product times the outer normal, which is 0. So this is not 0, but this is 0. This we just get as a conclusion. So contradiction. Yeah, contradiction. So there cannot exist a solution. Yeah, because for any solution we get a contradiction. Yeah, and this implies that there is no solution. So we indeed get that there is no solution. Yeah. Okay, step 3, contradiction. So there is no solution on a neighborhood of 0, 0. Okay, now we want also an example of with real coefficients. Yeah, and let us explain how we can obtain an example with real coefficients. Yeah, so how we do this. So we have our solution, and our differential equation was this operator. Yeah, this was U. Okay. Now we observe there's this operator. Sorry, once more. It's with a plus. Yeah, so if we combine this with this operator and then calculate this, one has to be a little bit careful because this derivative here, this applies also to the x, not only here to the y. And for this reason, it's not just this square of this times this, also this times this, minus this times this, but we also get this extra term, yeah, which comes from the derivative which acts here. Yeah, so So the derivative which acts here just gives a dy. And in the second term, we get the same term with a minus. So altogether, we only get this operator. Yeah, we get this operator, which is now a real differential PDE. Of course, it's now fourth order real PDE. But if u tilde is any solution of this equation, then you see that u, where we just take this expression, solves the other equation. So we see we don't have any solution of this equation. Yeah, okay, maybe I just do the calculation to explain how one gets this here. Minus ix dy. I first do the calculation for the first two and abbreviate this, of course, by dx plus ix dy. Okay, what we get if we calculate this expression, yeah, what we get here, of course, we get this and this. So this is dx squared. Here we get minus and e squared is plus x squared dy squared. And now be careful. Now if we apply this operator to this x, yeah, then we get plus x times dy. Okay. And now if we reverse the order, yeah, dx plus ex dy times dx minus ex dy. Okay, what we get in this situation, then we get dx squared. Of course, again, plus dx x squared times dy squared. But this time, yeah, we get a minus x dy. Okay. And now, so this operator is this operator times this operator. Yeah? This operator times this operator. And then we can write this in, so we can write this as this operator times this operator. And then we see that that if we multiply this out, yeah, then we get, of course, the y, of course, cancels. Yeah, we take the derivative. Here, this, of course, this term and this term is not there anymore. Yeah, okay. So now we should take this operator, this operator times this operator, yeah, because this we can write as this two products, and the second factor with this gives this two products. So all together is this operator times this operator, yeah, and then we get, of course, this square. Okay, if we multiply this out, we get then some terms which comes here from this, but this we don't calculate. Here this is just the square plus this operator. And this operator, of course, commutes with this operator, because here is only an x, and this operator. Yeah. So dy commutes with this operator, so we only get this. Yeah. So this was the final calculation. So and then we have shown this finishes this section 2.3. So let's recall what we have done. We presented an example of an PDE with smooth coefficients which has no solution in the neighborhood of one given point. Yeah, and this example is quite tricky. It uses some results of complex function theory and combines it with some nice symmetry considerations. Yeah, so symmetry considerations together with tools of complex function theory. Of course, we do not assume that you all have heard complex function theory. Also, for those of you which didn't know complex function, we just take this as a result, and this will be not part of the examination. That you don't have to learn how this follows, yeah, how the proofs of this function theoretic statement goes. Yeah, this you don't have to know. Okay, thank you.